Talking about animations, it's finally time for us to add them into our system. Not only will they make our system look better, they will also make it possible for us to transition to the states that required animation events. We have already downloaded our animations before, so we are basically ready to use them. In case you haven't, make sure you do it first. In Unity, to control our animations, we need to create an Animator Controller and also add an Animator component to an object. The Animator Controller allows us to add transitions between multiple animations as well as set the conditions for those transitions. The Animator component allows us to set the necessary data for those conditions through code, or even play or stop a specific animation. In other words, it allows us to control the Animator Controller through code, among other things. It's also the component that allows us to specify what's the Animator Controller of a specific game object. We'll be adding our Animator component to our character model, so select it in our Player game object. In here, simply click on Add Component and search for Animator. When that's done, simply add it by double-clicking on it or pressing Enter. I'll set the Animator Culling mode to Cull Update Transforms. Simply put, Culling mode translates to what should animations do when they are not on camera. With our option, it will stop playing the animation when the object exits the camera, but still calculate where it should be so that the next time it enters the camera, it will start playing the animation at the right frame as if it never left in the first place. With that done, we now need an Animator Controller, so go to the Player Animations folder and create a new folder named Controllers. Inside, we'll create a new Animator Controller by right-clicking in the project window and going to Create Animator Controller at around the middle area. I'll name it Player Animator Controller. When that's done, select our character model and drag our Player Animator Controller to the Animator Component Controller field. Double-clicking our controller asset should open the Animator window. I'll leave it docked right next to our Input Actions window. Now, if this is your first time using an Animator Controller, this window is likely quite strange to you. While we won't be going through every available option or feature, we'll at least go through what we need to know. The graph in the middle represents the area where our animations and transitions will stay. You can move it around by using the mouse middle button. Go ahead and open up the Player Grounded Clips Animations folder. Then, drag the idle animation to this middle area in the Animator window. Unity automatically creates a rectangle for us. This rectangle is called a state. If we click on it on the right side, we shall see our idle animation assigned to the motion field. Unity also named our state the same as our dragged animation. With that, we know that in the Animator Controller we can have states that may have an animation attached to them. We can create a state without dragging an animation by right-clicking on the graph area and going to Create State and Empty. We can rename it using the top field, and we can attach a motion or animation if we want. So, states can represent animations if a motion field is attached, and it is through them that we'll add transitions to other states. A state with no motion attached to it can be used as a transition intermediary, such as enter this state without animating and then check which state we should transition to next. To add a transition to another state, simply right-click on the state we want to transition from and choose Make Transition. Then left-click on the state we want to transition to. This will create a transition from one state to another. We can see all of the transitions from the selected state to other states on the transition field, or we can click a specific transition line. In this transition, there are a few options that will be important for us to know, some which are within the settings foldout. The first one is the Exit Time option. Simply put, this means that the transition will only happen once the animation of the state we are transitioning from is finished. This leads us to the Exit Time option, which controls what percentage of the animation needs to be finished for the transition to happen if we have the Exit Time option enabled. In this case, we aren't waiting for the whole animation to finish, but instead 75% of it. We'll be disabling the Exit Time option for all of our animations, so this won't really matter too much for us. The next important option for our use cases is the Transition Duration option. This is simply how long does it take for this transition to happen. The default 0.25 value means that it will take 0.25 seconds to transition from one state to the other. A value of 0 will make it an instantaneous transition. Something to note here is that Unity seems to blend both state animations when there is a transition duration. This is cool because it makes our transitions look smoother. Of course, a big duration will also mean it will take a long time to animate a player with a second state animation. A value of 0 would also make it so there is no blending whatsoever and would make it a snappy animation transition. Later on, we'll need to be careful when using animation events and setting up an animation duration, but we'll understand why whenever we get there. The last important option for us is the Conditions field. Much like the name entitles, this specifies the condition that we need to fulfill for this transition to happen. This is what we'll be using to know if we should transition from a state to another. Now, we do need something to condition with. That something being a value, like a boolean value or a float value, which will allow us to add conditions such as transition if we are walking or transition if the speed is over 5 units. This is what the parameters tab at the left side of the window is for. To add a parameter, we click on the plus icon and choose the type of value that we desire. Throughout all of this series, we'll have one of our values be a trigger, while the rest of them will all be booleans. For our movement system part, we'll only be needing booleans. Let's add one. In our conditions, if we now add a new condition, our new boolean parameter should show there with a dropdown to choose if the parameter should be true or false for this transition to happen. That's mostly all of the basics we'll need to know about the Animator Controller. However, right now, if we were to drag all of our animations into this area and make the necessary transitions, it will very likely end up being an horrendous mess, which people often call the Animator Web. We'll be learning one of the two things that can help us organize things better, which are substate machines. We won't be taking a look at blend trees, but we'll at least learn how to make our substate machines reusable. Of course, while this will reduce the amount of webs one area has, in a big game with a lot of animations, this will likely still cause an animator web. There are probably a few assets out there, both free and paid, that can swap this animator system from Unity with a cleaner solution, but we won't be using any. In case you are wondering what blend trees are, they are a nice way to blend between animations often used in things such as movement, where you have a different movement animation per direction. If your project is one of those, it will likely be worth it for you to go learn a bit more about them. Now, regarding about what are reusable substate machines, they are simply normal substate machines made in a way that we can copy them into other Animator controllers without caring about what transitions to that specific substate machine exist, nor what transitions that substate machine has to the outside. It will likely become a bit more clear what this means when we start doing them. To create a substate machine, we simply right-click in the main area and select Create Substate Machine. I'll name this one we have just created Grounded. Feel free to remove the other states we have added. To go inside of this substate machine, we simply double-click on it. To go back, we either double-click on the Up substate machine, or we click once at the top in the Base Layer tab. You might also have noticed that substate machines are represented by a diamond-like rectangle shape compared to the rounded rectangles that represent normal states. Inside of this substate machine, we can create other states or even other substate machines. We are going to be doing both as our animations will be organized much like our folders are. So start by creating 3 other substate machines. Moving, stopping, and landing. For our normal states, we'll drag our idle and dash animations to this window area. Let's start by updating our moving substate machine. To do that, enter on it by double-clicking it. Then open up our grounded moving animation folder and drag all of the animations here. I'll organize them from the left to the right, following walk, run, and sprint. I'll also go ahead and organize the default states and substate machines from top to the bottom, where the up state and the entry node will be on top, and the any state and exit nodes will be on the bottom. Because dragging our animations automatically sets the states with all the data we need, all that's left to do is to set their transitions. When we have dragged our animations in, Unity already set up a default transition to one of them, which is marked by a yellow arrow. A default transition means that when we enter the substate machine and no other conditions from the entry node are valid or true, it will always enter the default transition. This is why if we select that yellow transition, there is no conditions field or any field at all. If we wanted to change this default transition to some other state, we would right-click on the entry node and select Set State Machine Default State, and choose a state we want to transition to by default. We'll set it to our run state, so if yours isn't, make sure it is. Now, from our previous transition code, we know that walking can transition to running, and running can transition to walking. But none of them can transition to sprinting, as only dashing transitions to sprinting. We also know that while sprinting can go to both running and walking, in Genshin it transitions to running, and then the running state takes care of transitioning to the walking state. Knowing that, create a new transition from the walk to the run state. Then, create one from the run to the walk state. Finally, create another one from the sprint to the run state. We now need to set our conditions for each of these transitions, so we need to create parameters. In the Parameters tab, create 3 new parameters: is walking, is running, and is sprinting. If you haven't deleted the previous parameter we created, feel free to do it now. When that's done, add these to the corresponding transitions. So, walk to run will have is running is true, run to walk will have is walking is true, and finally, sprint to run will have is running is true. That's it for our transitions between the 3 states. But why exactly did we create our isPrinting parameter if we are not using it? The reason why is because states outside of this substate machine might want to transition to a state that's inside of this substate machine. Such is the case of the dash state, which can transition to the sprint state. Whenever a transition happens from the outside of this substate machine to its inside, it will first arrive at the entry node, which then takes care of transitioning to the correct states. So add a transition from the entry node to the walk state and another one to the sprint state. Then add the condition of walking is true and the condition of is sprinting is true accordingly. If none of these conditions is valid, then our substate machine will transition to our run state, as it has the default transition set to it. Note that this also means that we only need the isRunning parameter because we need it in the transitions conditions between the three states themselves, as the default transition doesn't require it. There's now only one transition left, which is a transition from our states to the outside states. Now, normally people will likely go ahead and add transitions from these states directly to the outside states. This can be done by creating a transition to the up node. This should bring up a menu that shows every existing state and substate machines that are outside of this substate machine. While this works fine, this is basically setting up a dependency, which makes it so that this substate machine is no longer reusable. The reason being that we are directly transitioning to a state or substate machine from the outside of this substate machine. So if we copy the substate machine elsewhere, we would also copy those dependent transitions. This isn't what we want. What we want is to know that we indeed can transition to a state from the outside, but we want to decide what that state is outside of this substate machine. When we copy a substate machine that defined its transitions outside, those transitions won't be copied with it. However, we do need a way to tell our substate machine states that they can transition to the outside, without directly telling them what states they can transition to. The way we do that is by using the exit node. When a transition goes to the exit node, it will exit the substate machine and stays in the up substate machine, checking for whatever conditions it has. This makes it so that we can add our transitions outside of the substate machine, which means that if we want to add a new transition, we don't need to update the insides of a substate machine and can simply add a transition outside. Knowing that, create 3 new transitions, one from each state to the exit node. For our condition, we'll create a new parameter of type bool and name it moving. I'll move this parameter up. Then add it to every condition of our new transitions and set it to be moving is false. Note that we need to add it one by one, as selecting all of them doesn't really edit them all. Now, this moving parameter is also how we are going to be transitioning to this substate machine without caring about what states are inside. If from the outside we create a transition from a state to the substate machine and make its condition be moving is true, we can easily add or remove states from the inside of the moving substate machine without breaking existing outside transitions, as those outside transitions do not care at all what states we have inside, but simply that they need to transition to the substate machine when we start moving. That's it for our moving transitions. But we should of course set each transition setting correctly. So, one by one, disable the sExitTime option, which renders the exit time field useless, and leave the transition duration as 0.25. You might have noticed that some of our transitions are grayed out and don't allow us to set any settings. This happens when our transition is an entry transition. The settings of these transitions are set through our exit transitions. This simply means that when we enter a substate machine through a transition from the outside, its entry node transition settings were defined by that outside transition. So, for example, our moving substate machine exit transitions define the settings of our future stopping substate machine entry transitions. This makes sense because our exit transitions are the states we are transitioning from. For example, we'll be transitioning from the walk state to an outside state, and the walk state defines that there should be no exit time when we are transitioning from it. Of course, this also means that the entry transitions are the states we are transitioning to, so they shouldn't be the ones deciding the transition settings. That's it for our moving substate machine, so in the up substate machine, let's add transitions from the other states to this one. Before we do that though, I'll organize them a bit. I'll add the landing to the top left, the moving to the bottom left, the stopping to the top right, the dash to the bottom right, and the idle to the middle up. I'll also make sure that the idle state is the default state. The states or substate machines that can transition to the moving substate machine are landing, stopping, idle, and dash. The condition for all of these four transitions will be moving is true. Now you might have noticed that only our states have a white transition. This is because in normal states there are no exit transitions as there is no exit node, so our created transition can be considered their own exit transition. This means that we need to define their transition settings here. Because of that, in both the idle and dash transitions, we'll be disabling the exit time option. Make sure the transition duration is always set to 0.25, which shall be the default value. As a test, if we were to duplicate our moving substate machine, it will come without the transitions, which basically makes it so that we can copy it to other Animator controllers. As a side note, if you are wondering about the any state node in the substate machine, it means any state in the whole Animator controller, and not for that specific substate machine. As far as I know, there is no built-in node for the latter. That's basically all we need to know regarding our Animator controller. So all we need to do now is to add the remaining animations and their transitions. Let's start with our stopping substate machine, so double click on it to open it up. Then open the stopping clips animations folder and drag the animations into the substate machine. I'll order them as medium, light and hard stop, as I like to keep the default transition in the middle, which will be our light stop state. I'll also organize them before we keep going. When that's done, I'll add a transition from the entry node to the other two states, as all the states in this substate machine can be transitioned into from outside states. Then add a transition from all states to the exit node. We'll not add any transition between the three states as they can transition between each other. In every white colored transition, disable the exit time option. We'll only need 3 new parameters here, so add in stopping is medium stopping and is hard stopping. From the entry node to the states, add the condition of is medium stopping is true for one and is hard stopping is true for the other. From the states to the exit node, add the condition of stopping is false. We don't need a parameter for our light landing state because it uses a default transition, which doesn't require a condition, and also because no other state inside of the substate machine transitions to it. That's all we need here, so go up to the up substate machine. The states that will be able to transition to this substate machine are moving and dash. Make sure you are transitioning to the substate machine and not a specific state. The transition conditions are, of course, stopping is true. Again, select the white transitions and disable their as exit time option. For our last grounded substate machine, we have the landing substate machine, so open it up. Open up the landing folder and drag the existing landing animations here. I'll organize the area here as well. We'll make the light landing the default animation. Because it is the default one, we don't need a condition nor a parameter, so simply transition it to the exit node. Disable the as exit time option from the transition, and then create a new parameter named landing. Add a condition of landing is false to the transition. Add the transition from the entry node to the other two landing animations. Create two new parameters, is rolling and is hard falling. Add them in their respective conditions in the entry transitions. Then add another transition from the other two landing states to the exit node, and add the condition of landing is false to both transitions. And tick the as exit time option in both of them as well. That's really it, so go to the up substate machine. The following states can transition to this substate machine: jumping and falling. Of course, we don't yet have our jump and falling states here, but that doesn't really matter, as all that we need to do is to add a transition from the entry node to the landing substate machine with a condition of landing is true. This is the good thing about reusable substate machines. We don't need to care what states from the outside transition to it. One thing you might have noticed is that inside of our substate machines, our up substate machine might transition to the entry node. These are the transitions of the outside states or substate machines to this one, but we don't need to worry about them, as if we duplicate a substate machine, they won't be present in the new one. All that's left now for our grounded states are our idle and dash states. Because these aren't substate machines, we don't really need to do anything else besides adding their transitions. Knowing that, we'll be able to transition to the idle state from landing and stopping. The other two will go to the stopping state and not to the idle state. We need to create a parameter for this state, so add a new boolean and name it is idling. I'll drag the parameter to the top. Then add the condition of isIdling is true for both transitions. Because no states directly transition to this one, none of them are white-colored transitions, meaning that their settings were set from the respective sub-state machine transitions to the exit node. For our dash state, we can transition from landing, stopping, moving, and idle. Create a new parameter of type bool named isDashing. I'll move it under the isIdling parameter. Then add the condition of isDashing is true to every transition. For the transition between the idle state and the dash state, we'll also need to disable the sExitTime option. That's it for our grounded substate machine, so we now need to do our airborne substate machine. Of course, every grounded state can enter the airborne state, known as jumping state and also the falling state. This means that we need a transition to the exit node from every state to be able to transition to them. So go ahead and add a transition from every state to the exit node. For the condition, add a new bool parameter named grounded above all others. And set the condition for each transition to be grounded is false. For the white transitions, make sure you also disable the sExitTime option. Back into our base layer, add a new substate machine. I'll name it Airborne. I'll organize them a bit. All nodes can be above the entry node as we won't use them. I'll also place the Airborne substate machine a bit to the left, as later on in the series we'll add a swimming one to the right. We'll need to transition from and to the grounded substate machine, so add a transition from both sides. Then create a new bool parameter named Airborne. For the transition from the grounded substate machine to the airborne substate machine, we'll add a condition of airborne is true. For the opposite transition, we'll set the condition of grounded is true. In my original system, I also added the current state is false condition due to a bug that I don't really remember. But I couldn't seem to get any bug with the way we have things right now, so I'll leave it as is. If you do end up finding any bug regarding animations between different substate machines, then you might want to try and add that extra condition. Unless my brain isn't thinking correctly though, there should be no problems, and it's possible that the bug was fixed through finishing the system. Opening the airborne substate machine, we need to drag our jump and fall animations here, so make sure you go to the right folder and drag them in. I'll organize them a bit. We'll make our jump animation the default animation. We'll be able to transition from the jump state to the fall state, so add in a new transition to it. Then create a new parameter named isFalling, and add it as a condition to the transition we have just created. Of course, it transitions when it is true. Make sure to untick the sExitTime option as well. Then add another transition from the entry node to the fall state with the condition of isFalling is true. When that's done, add a transition from both animations towards the exit node, with the condition of Airborne is false in both of them. Again, make sure they have the sExitTime option unticked. With that done, our animation controller is finished, and all we need to do now is to set the parameters to either true or false through code, and also set up our animation events. Let's start by setting our parameters first. We'll be doing that using the animator.setBool method. This method accepts a string, which is the name of the parameter, or an int, which is the ID of the parameter. The ID here is an hash that we can get from the string-to-hash method. If we pass in a string to the setBool method, it will call this string-to-hash method to transform it into the hash integer. That means that any setBool call with a string as the argument will need to do that conversion. Because of that, it will be way faster for us if we instead pass in that hash right away. Of course, we ourselves don't know that hash, but the fix for that is quite simple. We simply need to cache that hash once by using the string-to-hash method and then pass it into the setBool method. This ensures that the string-to-hash method is only called once per parameter, instead of being called once on every setBool call, which should lead to a better performance. Of course, this all assumes that the string-to-hash method doesn't cache the data into an hash set. If it does, then there shouldn't really be much or any performance difference. However, regardless of it caching it or not, it's still a great idea to cache it in, as that makes it possible to change its name through the inspector whenever we want, and the changes will be seen across all usages. To do this, in Unity, open up the Player Data Scripts folder and create a new folder named Animations. Inside, create a new C# script named Player Animation Data. Open it up and remove the default methods and inheritance, and make the class serializable. We'll need two things for each parameter: its name, which is the same as the one we have set in our Animator Controller, and a property to store our hash. Let's start with our names. I'll create an header with a text of state group parameter names. And then type in serialize field, private, string, grounded parameter name, and default it to grounded. Then duplicate this line 4 more times and swap grounded with moving, stopping, landing, and Airborne. Make sure the actual strings have the exact same name as the Animator Controller parameters, even the uppercased letters. I'll now create another header with the text of grounded parameter names. Copy one of the lines above and paste them here. I'll paste it in a total of 10 times. When that's done, we'll swap the variable names and default values with idle and is idling, dash and is dashing, walk and is walking, run and is running, sprint and is sprinting, medium stop and is medium stopping, hard stop and it starts stopping, roll and is rolling, hard land and hard landing, and fall and is falling. Remember that some of our states don't have a parameter as they use default transitions, so we don't need to add them here. If you ever intend to add parameters for them in the future, then you can also create a variable for them if you want to. But I think you need to make sure they also exist in the Animator Controller. That's it for our grounded strings, so we now need to create our Airborne strings. To do that, copy the first two lines including the header. Then paste them in and swap grounded with Airborne, and set the variable name to be fall parameter name, and its value to be is falling. With that done, we now need to create properties for our hashes. To do that, create a new public property by typing in public int grounded parameter hash and give it a private set. We don't need the field serialized field here, as we don't need to set these through the inspector, as they are generated by the string to hash method. Duplicate this line for each variable we have above and rename them accordingly. That's done, so we now need to initialize them. To do that, create a new method by typing in public void initialize, and inside type in grounded parameter hash equals to animator.string to hash and pass in grounded parameter name. The animator here is the animator class itself, and the string to hash is simply a static method. Do the same thing for every single parameter. When that's done, make sure the default names are correct and save. If you saved and they weren't correct, make sure that you update them correctly in the inspector as well, when we add it to the player script. To add it, open up the player script. In here, create a new field, serialized field, public player animation data, animation data and give it a private set. I'll also add in a field header with the text of animations. Now in the awake method, call in animationData.initialize. We now have a reference to our parameters hashes. Of course, we'll need to use the animator setBool method, which means we need a reference to our animator. To do that, create a new property by typing in public animator with a private set. Then, in the awake method, type in animator equals to getComponentInChildren of type animator. Note that getComponentInChildren first searches in the parent and only then in its children, which doesn't really make sense given the name. If you wanted it to search only in the children, then you will probably iterate through its children with the getChild method or through its transform, if that works. Because we really only call it once, and because we are searching for the animator of the player, which there should likely only be one, I'll leave it as is. With that, we'll need to start setting our animator parameters. To do that, first open up the player movement state script. We'll create a method here to not need to call the setBool method every time. So in our reusable methods region, create a new method by typing in protected void start animation and pass in int animation hash as a parameter. Inside, call in statemachine.player.animator.setBool and pass in animation hash and true. We'll also need one to set it to false, so duplicate this method and swap the start with stop and the true with false. With that done, we simply need to call these methods in each state enter and exit methods, both to start and stop respectively. So start by opening up the player grounded state script. In the enter method, type in start animation and pass in statemachine.player.animationdata.groundedParameter hash. When that's done, copy this line. Then override the exit method and paste the line we have just copied. In here, simply swap start animation with stop animation instead. That's all we need to set a parameter value, so all that's left is to do the exact same thing for the rest of the states. So open up every state and call both methods for the states that have a parameter. That's all we need to do, so when you are done doing that, save everything and go back to Unity. If we enter play mode, our animations should now be playing whenever a state changes. However, you might be noticing a problem when doing something like running and then jumping. This seems to happen because there is a prioritization order for the transitions, likely because you can have two conditions being true at the same time, so Unity needs to prioritize one of them. In this case, if it happens to you, it's likely that you are prioritizing a transition to something like a stopping state or idle state instead of prioritizing to the jump state, or in this case the exit node. To fix that, exit play mode and go to the Animator Controller. Clicking any state, we should see the transitions it has. We can drag them and set their order by holding the two small bars icon. I'll be changing their order to be exit, moving, dash, stopping, landing, and idle in that order. Do it for every ground state. For the Airborne states, we'll focus on the exit one and then on the fall. This should now make it work more correctly. Of course, we still need to take care of our animation events. To do that, exit play mode if you entered it, and select the character model. Then, in the Project Window tab, right-click to add a new tab and select Animation in case you don't have one open. This tab shows the animations that are in the Animator Controller of our currently selected game object. This is where we can add our animation events. If we move to any frame that we desire and click on the last small icon with the tooltip of Add Event, we'll add an event to the selected frame, which should show in the frame column. Clicking on it shows us the animation event window where we can select a public method to call. We however have two problems here. The first problem is that we have no way of calling our state events, as only methods that are part of a script in the same game object as the animator component show in this drop-down list. Because our model is separate from our player, this means that we can't access our player script code. Furthermore, none of our states are mono behaviors, so it isn't possible for us to add them as components, which means that we have no way of directly calling their methods. The second problem is regarding our animation events and the transition duration, but we'll take a look at it after we fix the first problem. To fix it, we can create a public method in our player script that calls a state machine animation events methods. However, our animator currently sits on a child game object of the player game object, which again means that we have no access to our player script methods. To fix that, we'll have to create a new class that references the player and calls its public methods. We can then attach that script as a component of the character model, which allows us to use it in our animation events. So start by removing the animation event we have just added by right-clicking it and pressing delete. Then open up the player script. In here, we'll need to create one method for each of the animation events methods, so type in at the bottom public void onMovement state animation enter event, and inside call in movement state machine dot onAnimation enter event. Duplicate this method twice and swap enter with exit for the first one, and then enter with transition for the second one. When that's done, save it up and go back to Unity. In here, navigate to the Player Utilities Scripts folder and create a new folder named Animations. Inside, we'll create a new C# script named player animation event trigger. Open it up and remove the default methods. Because we'll add this as a component, we need to keep the monoBehavior inheritance. In here, create a private variable of type player named player. Then, in the awake method, get it by typing in player equals to transform.parent.getComponent of type player. There's also the getComponentInParent method, but that one also calls the getComponent in the GameObject we call it in, much like the getComponentInChildren method, so we'll use our current solution. When that's done, we'll create a new method to call the events by typing in public void trigger on movement state animation enter event. And inside, call in player.onMovementState animation event. Duplicate this method twice and swap enter with exit for the first one and enter with transition for the second one. When that's done, save it up and go back into Unity. Then in our character model GameObject, add the player animation event trigger as a new component. Back to our animation tab, we can now add in our animation events. Click on the dropdown on the left and select Dash. We'll need to transition to our sprinting state here, and we'll do it around halfway into the animation. So select a frame around the middle, to which I'll choose the 0:11 mark, and add a new animation event. Then select the transition event method in the animation event window. Note that you can add multiple animation events to the same frame if you wish to. When that's done, open up the dropdown again and select Light Stop. The stopping states will simply transition to the idling state at the end of their animation. So around the last frame or around the 1 second mark, as the animation is somewhat coming to a stop here, we'll add a new animation event. Call in the transition event method. Do the same in our medium stop animation. In our hard stop animation, we'll add it a bit earlier around the 0:20 mark. Then in our light landing animation, we'll have an animation event transitioning to the idling state at the last frame. Next, in our rolling animation, add a new animation event around the last frame. I'll place it at the 1:02 mark, transitioning to the medium stopping or moving states. I added it at around the 1:02 mark as that looked a bit better for me. If the transitions don't look too good, you can always add them earlier or later as you desire. Next, for our hard landing animation, we'll need two events. One will be for enabling our movement input, while the other one will be to go to the idling state. I'll add the first one at around the 1:11 mark, which should be around when we are getting up, and call in the exit event method. Then I'll add the second one at around the 1:25 mark, and call in the transition event method. And that should be it for our animation events. However, we still need to talk about our problem regarding animation events and transition durations. Let's enter play mode to see what the actual problem is. In here, let's dash, wait a bit and dash again. We can see that our player just stopped dashing right after our second dash. The reason why is because animation events can still be called when we are in the middle of a transition. This is possible because while we are transitioning, our previous animation is still happening or running until we fully transition to the other. An even bigger problem with this is that we'll already be in our new state, so the event that will be called will be the one of that new state. In our case, we entered the dashing state and then the hard stopping state, and then dashed near the animation event of the hard stop animation. Because in code we have already swapped to the dashing state, the animation event ended up calling the dashing state event instead, and entered the hard stopping state again, as that's what we do in the dashing state transition event method. Thankfully, we can easily fix this by not calling an animation event if we are in the middle of a transition. To do that, open up our player animation event trigger script. Then, create a new private method that returns bool named isInAnimationTransition. We'll add a parameter of type int named layerIndex and default it to 0f. While we won't be using layers here, the method we'll call requires it, so it's always nice to have the possibility of passing it in. To be honest, I don't really know much about layers, but this index is the index of the layer our animations are in the Animator Controller, which should be the first and only one, so it's the index of 0. Inside of this method, simply type in return player.animator.isInTransition and pass in layer index. Then, in all of the other methods, before we call our player animation events, check if isInAnimationTransition and return if that's the case. Copy the if statement to the other two methods as well. When that's done, save it up and go back to Unity. Entering play mode, we shall no longer have this problem, and our animations and transitions should all be working fine. If you did want to call the previous state animation event, you could do that by adding a new variable to our state machine that held the previous state and simply call the previous state animation event method instead. Of course, you will need a new method in our player script to do that. Also note that if our transition duration was 0 seconds, this problem wouldn't happen as the transition will be instantaneous. Someone also wondered if we were gonna add the double animation that Genshin offers, but I have decided when I started trying to replicate this system that I will not do it. In case you are wondering what do I mean by double animation, it's simply that Genshin seems to have two animations in certain states, like jumping or stopping. If we take a look at it, we can see the arms and legs that go to the front can be different. I'm not sure if they do this using IK or simply have two animations, but the leg and arm that go to the front seem to depend on the foot that was at the front as well. For example, if you jump when your right foot is ahead, you seem to jump with the left knee forward. It does seem to only happen after the feet has touched the ground, as if you jump before that you'll jump with the same side knee forward. According to a forum post, if you are using a generic model, which we are for no particular reason besides me not really understanding very well how models and animations work, we can know which foot is at the front by using animation events. You will simply go to each step in the moving stakes animations, for example, and whenever the foot touches the ground in the animation, call in an event that sets a variable that tells you what foot is currently at front. If you end up using a humanoid model, which is probably what we should have been using, you can know it using the animator pivot weight variable. Although it seems that this doesn't work for some if they have the root animation option enabled, and they had to use something else like the animator getBoneTransfer method. For the animations itself, it's possible that they do it with IK by setting where the knee should go, or you could flip the animation and add both animations to an array or simply two variables, which you will then choose an animation depending on which foot is currently at the front. Of course, we won't be doing it ourselves, as that's what I've decided myself before. Regardless, our animations should now be working fine, and we should now be able to transition to every existing player state.